The umask command is a feature in Unix and Unix-like systems that controls the default file permission settings for newly created files. It communicates with the umask system call, where the actual mask value is stored at the operating system level. This mask, also known as the file mode creation mask, limits the permissions granted to new files based on its binary values. Each bit in the mask corresponds to a specific permission: read, write, execute, determining whether it is allowed or disallowed when a file is created. The umask essentially acts as a filter that removes permissions during the file creation process, stripping away access based on the set bits in the mask. File permissions can be altered after creation using commands like chmod. Each process in the operating system retains its own umask value, which is inherited by child processes when they are spawned. While the umask primarily influences file permissions at the time of creation, it plays a role in determining permissions when the chmod command specifies mode options using symbolic mode without indicating a user class reference. This functionality is specific to Unix-like systems and is outlined in the POSIX standard. Before the introduction of the umask feature in Unix systems circa 1978 in the 7th edition, developers employed various methods to restrict access and enhance security. The umask capability was designed to offer flexibility to sites, groups, and individuals in selecting their preferred default permission settings. The umask command, when called without a parameter, displays the current mask in either octal or symbolic format, dependent on the implementation. In some shells, opting for the S option enables the output to be in symbolic notation. By setting an octal parameter, one can adjust the stored mask to the specified value. When entering fewer than 4 digits, leading zeros are assumed. However, if more than 4 digits are input, the command will fail. Notably, umask does not support the leading zero convention used in languages like C to denote octal format. The final 3 digits in the octal representation determine the permissions for the user, group, and others correspondingly. Should a 4th digit be present, the initial digit focuses on special attributes such as setuid, setgid, and the sticky bit. When supplied with a parameter in symbolic form, umask alters the mask so that newly created files can have certain permissions added or removed. The logic of this symbolic representation is inversely related to the mask value. Adding a permission clears the corresponding bit in the mask to allow that permission when creating a file, while removing a permission sets the associated bit to disallow it in new files. Symbolic notation changes are expressed as classes podczas operations, allowing for multiple expressions separated by commas, with the final expression ending in a space. This symbolic syntax is incompatible with the C shell's umask command due to differing behaviors. Classes denoted as U for user, G for group, O for others, or combinations thereof, can be selected. In the absence of specifications or for A, all classes are chosen, akin to UGO. The operator defines how the mask is adjusted. Plus allows specified permissions, denies permissions, and ACORS allows specified permissions while disallowing unspecified ones within the class. Various operations can be permitted or forbidden using symbolic notation, such as reading, R, writing, W, executing, X, special execute, X, setting setuid, judge S, and sticky bits, T. Commands like umask A+war grant read permission to all user classes without altering the rest of the mask. Conversely, umask AX prohibits execute permission for all user classes, but leaves the rest of the mask unchanged. For instance, umask ushad.go enables read and write permission exclusively for the owner, whereas forbidding all permissions for the group and others. Different examples showcase how creating files with specific permissions can be achieved using umask, illustrating its flexibility in managing file permissions. The table provided showcases the impact of each digit in the umask mask on the permissions of a newly created file in a scenario where the default permissions are set to read, write, and execute, RABWX. The umask value is applied by first negating it, then performing a logical AND operation with the default file mode. This process determines the resulting permissions for the newly created file based on the umask value. Typically, the umask mask is primarily utilized during file creation. Nevertheless, in specific implementations of the chmod command, when utilizing symbolic notation without specifying a user, the mask is applied to the requested permissions before applying them to the file. This can be seen in examples where the umask value is set, then permissions are altered using the chmod command, reflecting the impact of the umask on the resulting permissions of the file. Furthermore, within the Linux kernel, various file system drivers like FAT, HFS, HPFS, NTFS, and UDF support a umask mount option. This option regulates how disk information translates into permissions on the system. The umask mount option operates differently from the per-process mask detailed earlier, although the permission calculations follow a similar underlying principle. Additionally, some file system drivers offer the functionality of distinct masks for files and directories through mount options, like fmask.